Just look around you for a second. I bet you can see some concrete. It's literally everywhere, right? It's the foundation of, well, everything. Our cities, our homes, our whole modern world. But it all starts as this simple powder. And hidden inside that dust is a whole secret world. A microscopic universe that decides if a skyscraper stands tall or a bridge just crumbles. So, how is it possible that you can use the same basic ingredients and get completely different results? Why is one batch of concrete super smooth, easy to pour, and sets like a rock, while the next one is just a lumpy, useless disaster? Well, the answer isn't just about the recipe. It's about getting to know the secrets of the powder itself. I mean, the recipe itself looks almost ridiculously simple, right? Sand, gravel, water, cement. But the real magic, the science that makes or breaks it, happens with stuff you can't even see. We're talking about particle size, their shape, how much surface area they have, and even how much they like to clump together. This is where it all happens.
Okay, so if we want to build better concrete, we have to become detectives. We got to understand the secret life of this powder. And that means measuring all these invisible things with some serious precision.
All right, first up is something called particle size distribution, or PSD for short. The best way to think about it is like a census, but for dust. See, it's not good enough to just know the average size of a particle. You need to know the whole picture. How many really tiny ones are there? How many are medium? And how many are the big guys? So what? Why does this even matter? Well, it's pretty cool, actually. The smaller, finer particles have way more surface area, so they react with water a lot faster. This kicks the hydration process, that's the chemical reaction that gives concrete its strength, into high gear. So by controlling this mix of sizes, you're basically turning a dial that controls how fast and how well your concrete sets up. It's amazing.
Okay, but think about it. How in the world do you measure something that's basically microscopic dust? Well, scientists have some pretty slick tools, and the first one we're going to look at is called laser diffraction.
The idea behind it is actually genius and pretty simple. You take a laser, you shoot it through a cloud of the powder, and then you just analyze the shadow it makes. It turns out bigger particles scatter the light in a narrow pattern, while the tiny ones spread it out all over the place. A computer just measures that pattern, and boom, it can calculate the entire size distribution.
But, of course, there's a catch. There's always a catch, right? The math for this laser trick only works if you assume every single particle is a perfect little sphere. And, spoiler alert, they are not. So scientists came up with this clever workaround. They call it the equivalent spherical diameter. Basically, they figure out the size of a perfect sphere that would have made the exact same shadow as the weird, lumpy particle we're actually looking at.
I mean, just look at these things under a microscope. This right here is why that whole sphere idea is a problem. They're all jagged and angular, totally complex. They're anything but spheres. So that equivalent spherical diameter, it's a really useful fudge factor, but it's something we absolutely have to remember is just an approximation.
And this is where things get really interesting. Because that assumption about shape, it starts to cause some real problems. The data we're getting doesn't always tell the whole story.
Okay, check this out. These two graphs, they're showing the exact same powder. Seriously. On the left, it's plotted by the number of particles. See that big spike with the smaller sizes? Now look at the graph on the right. This one is plotted by volume, and the whole story just flips on its head. A handful of those big particles take up so much space that they totally dominate the measurement. It makes the powder look way, way coarser than it really is. And there's another problem lurking here. These little particles, they love to stick together. They form these clumps called agglomerates. And to that laser we were talking about, a clump of, say, 10 tiny particles looks exactly like one single giant particle. This can totally throw off our readings. It proves that just looking at particle size isn't going to cut.
So if measuring size is this much of a headache, what do we do? Well, this brings us to another technique, a second tool in our toolkit. And this one helps us get around that whole shape and clumping problem by looking at texture.
It's called specific surface area, or SSA. Here's a great way to think about it. Imagine you have a flat sheet of paper. It's got a certain surface area, right? Now crumple it up into a tiny ball. The ball itself is way smaller, but the actual surface area of the paper, with all those little folds and creases, is still exactly the same. SSA is a way to measure that total, true surface area for a whole bunch of powder.
The old way of doing this, the Blaine test, was pretty crude. It just measured how easily air could flow through the powder. You miss all the good stuff. But the modern way? Oh, it's so much cooler. It's called the BET method, and it basically paints the powder with a super thin layer of nitrogen gas. We're talking 1 molecule thick. By counting exactly how many gas molecules it takes to cover every single nook and cranny, scientists get the true total surface area. It's incredibly precise. Now, getting this measurement right is a process. It takes a ton of care. First, you have to completely stop any chemical reactions that might be happening. Then, you have to gently clean off the surfaces of all the particles, getting rid of any stray molecules. And only then can you start that super precise measurement with the nitrogen gas. It just goes to show you how careful this science really is.
Okay, so let's recap. We've got 2 powerful tools. Laser diffraction gives us the apparent size, clumps and all, and gas absorption gives us the true surface area. They're both useful, but incomplete. The real breakthrough, the aha moment, is when you put them together. This is how we finally solve that problem from the beginning and start really engineering this stuff.
And, the researchers who wrote the paper we're looking at said it perfectly. You just can't use one of these on its own. You have to combine them. The particle size tells you what the laser sees, while the specific surface area tells you what's really there, texture and all.
And this is where it all clicks into place with one simple, powerful number, the agglomeration factor. Here's how it works. Scientists just compare the 2 numbers we've been talking about. They take the big, clumpy size the laser sees, and they compare it to the tiny, individual size they get from the surface area. If those 2 numbers are worlds apart, well, it can only mean one thing. That powder is super, super clumpy.
So, for example, the researchers looked at this material called calcined clay, and its agglomeration factor was over 40. That is a huge red flag. It's like a big flashing sign for engineers that says, hey, this powder is a clumpy mess. You're going to need to handle it with care. Maybe mix it really intensely or use special chemicals to get it to work right.
And this is why it all matters. By combining these measurements, we're not just cooking with a recipe anymore. We're engineering a material, right down at the microscopic level. And this is how you get concrete that's stronger, that lasts longer, that's way easier to pour and work with, and that's even better for the environment. It all comes from finally cracking the code on the secret life of dust.
Think about that for a second. We've taken one of the oldest building materials in the world, and we've totally unlocked its secrets just by mastering its tiniest little pieces. So my question is this. If we can engineer something as basic as dust with this much precision, what's next? What other limits are we about to shatter? And what is the world we build tomorrow even going to look like?